the inverse operation of it. All right, good afternoon, morning, evening, whenever you're watching this. Mr. Campbell and Ms. Walton here, trying to help you get through some learning if you are at home right now. We've been working on organizing and arranging real numbers, ordering them in different ways. And so one way we've ordered real numbers is from least to greatest, like if you had 1, 2, 3, 4, put them in order. Another way you're used to is ordering them from greatest to least. That's why that G through L is there. But I want you to think about something and consider if you ran into a question that didn't ask for least to greatest or greatest to least, but just said first to last. Here's why you need to think about that, because you really have to pay attention to the story if it says first to last. If the story is about a football game and you're supposed to rank different football scores, then the first place would be the highest score, the biggest number. But if it was a golf game, then the winning score, the first place score, if you will, would be the lowest score. Likewise, if we were trying to compare something in basketball, and then we would want the highest score to be in first place. But if you were running a race, then you would want the lowest time, because in a race, the lowest time wins. You want to get done fastest. So my encouragement on that is, regardless of the situation, the question that's asked, make sure you understand the story, because it may not always say least to greatest or greatest to least. It might word it in a different way. With that in mind, here's a question I want you to think about. It says the table shows the completion times of 4 runners in a race, and then it lists them right there, Joe, Ellen, Steve, and Patty, and they all have their times in the race recorded here, and they have different ways they're recorded. We've got a mixed number fraction right here. We have another one. We have a decimal up to 2 decimal places, and then we have a decimal only up to 1 decimal place. And somehow you have to figure out how to order those correctly. Now, if you're totally good with this, great. But if you're not, if that makes you a little bit nervous, then I would like to point you to this kind of structure right here. If you take Joe's number and you turn it into a decimal, it'd be 12.50. If you take Ellen's number, it's 12.09. And by the way, if you type Joe's number into a calculator, it actually says 12.5. But I'm adding that 0 because I want it to be comparable to Ellen's number. I want to see both numbers with both sets of decimals right there. And then Steve, likewise, if you put it in the calculator, it'll say 12.4, but I'm adding the 0. Patty, I'm adding the 0. And then I just look at them, I go, well, if this is a race, then I want the lowest time, right? That's going to be the fastest person, the winner. And Ellen got there first, followed by Steve, followed by Joe, followed by Patty. And that leads us right there to letter C as the answer. This is another question, and I'm not going to walk through how to do this one. I'm just going to remind you that you would take the 4 numbers up here, turn them into decimals on your calculator, list them out, and then order them from least to greatest, just like the question says. So you can pause the video here and work that out. And then, same thing with this question. Not going to work it out for you. I'm just going to point you to the right way to do it. 2 numbers are shown on the number line. Which value is not located between these 2 numbers on the number line? So you got to turn this into a decimal and write it down. Turn that into a decimal and then write it down. And then find out of all these choices, which one is not between these 2 numbers. So convert them into decimals, write it all out, make your list, and then the answer, I think, will become clear to you. So take a minute, pause this, look at it, work through it. Okay, now the answer is going to be revealed. So you can check yourself. The answer on this one is C. Question number 4. I like this one because it has a big long story with lots of words and stuff like that, and most of it doesn't even matter, meaning this. It's talking about plumbers and lengths of cylindrical pipes of radii and things like that. But at the very end, it just says, hey, can you just put them in order from greatest to least? Sure you can. So take all your choices, write them off to the side, turn them into decimals, and then put them in order from greatest to least. This is a pause point. Okay, so you paused it, you worked it. There's the answer right there, letter B. Hope you got it right. That's a little review on ordering numbers. Now, I'm going to ask you a big question. We've been ordering real numbers, but what are real numbers? Like, has anybody walked up to you and said, oh, my, I just love real numbers, and I'm so sad about all the non-real numbers that I see. Nobody's ever said that. You know why? Because you haven't seen any unreal numbers. A real number is anything you can think of, no matter how complicated it is, no matter how big it is or small it is. Everything that we know about and we talk about and you've ever seen in your life is a real number. You won't run into unreal numbers or imaginary numbers until high school. If you do, then. So just think, anytime I'm asked a question, hey, is this a real number? The answer is yes, and then it'll be good. You remember last week, or maybe about a week and a half ago, we went through this categorization and we said, hey, if these numbers have similarities, are they in the same category? And we tried to just experiment and put things in a place. And some of us did good on that. Some of us were a little confused. But we just had a little experience in that realm. And I told you we were going to come back and revisit it. So we're very close to doing that. And then we did an activity here. And the way we use this frame is we picked a student's name. I'm going to pick Joe right here. And we said Joe is a student in the class. And because Joe is a student in the class, we also know that Joe is in 8th grade math. And because we know Joe is in 8th grade math here in this building, then he attends Trinity Springs Middle School. And because we know he attends Trinity Springs Middle School, then he's also in Keller ISD. So all those things put together just get more and more specific the closer you get to the middle. But whatever is on one of these inner areas is also included in the larger areas, meaning 8th grade math students at this school are part of Keller ISD. And 8th grade math students at this school are part of Trinity Springs Middle School, obviously. And Joe is part of 8th grade math and Trinity Springs and Keller. So when you look on the inside information is also included in the bigger categories. But you can't go the other direction. You can't say, well, all Keller ISD students are named Joe. That wouldn't work. Or all Trinity Springs Middle School students are in 8th grade math. That wouldn't work. This is the central truth, and it is included in all the bigger truths. So keep that in mind when you think about the real number system right here. Any questions? Ms. Walton, we good?
Good.
Okay, she says we're good. Now we're going to look at the real number system, and I'm going to block off the outside edge right here because I really want to draw attention to something that confuses people. Everything inside this box is a real number. That means a rational number is real, an integer is real, a whole number is real, a natural number is real, and an irrational number is real. We'll get into that later, but just see from the outset, the way this thing is built, everything is inside the real number box. Some questions. You've got this chart on PDF on Google Classroom, so you can look at it. And it's asking you to try to consider why some boxes are smaller than others. It's asking you to consider if a number is a natural number, could it also be, or is it also an integer? And then third thing, do you think an irrational number is a real number? Why or why not? So take a minute and think through those things. Hopefully you printed this off and you can write down your thoughts on your paper at home. In class, we just took 3 minutes to think through that. So pause and think through that and write your answers. When you unpause, I will tell you that the class conclusions we came to were on the first one. Why do you think some boxes are smaller than others? Because there are less numbers in that category. So if we look here in natural numbers, there are less numbers that fit in natural numbers than there are integers and rationals and so on and so forth. And you'll see why in a minute. Number 2 answer, if a number is a natural number, is it also an integer? Yes, because natural numbers are inside the integer box. Go back and look at this and we say, well, natural is also inside integer, so yes, naturals are part of integers. And the last question, is an irrational number still a real number? And the answer is yes, because it is inside the real number box. So make sure you record that. Then we move on here and we are going to start looking at specific definitions of real, rational, irrational, integers, whole, and natural. And to do this, I'm going to call the esteemed Miss Walton up to the stage to help me. You have the pen.
All right, everybody. So we have 6 different definitions that we're going to look at. And as we go throughout these definitions. Obviously, I know you can read, but I'm going to read them out loud just for dramatic effect. So, a real number, like Mr. Campbell taught us, we have this entire box that everything inside this thing I'm highlighting are all going to be real numbers. So, makes sense when our definition says any and all real numbers that we know. Again, once you get to high school, you'll get into some crazy stuff that you don't even have to worry about this year. So, you can know that any numbers that we're going to work with as an 8th grade math student are going to be real. So, moving to our rational numbers, they are any numbers that can be written.
Miss Walton, I have a question. What does rational mean?
Rational. So, in life, you may have heard somebody say an irrational person, maybe. So, I would consider Mr. Campbell an irrational person. And
I'm not irrational. I'm just colorblind. That's it.
So, a rational and a rational and irrational. So, let me break this word down for you. So, if we have...
Yeah, on mine, you have to really press hard on it.
All right.
To be bored.
Rational. So inside the word rational, we have this word ratio. So a ratio can be written in multiple ways. Sometimes you can compare the ratio of teacher to student or girls and boys in a classroom. But a ratio can sometimes be written as a fraction like this. So a rational number is any number that can be written as a fraction. And this includes repeating or pattern decimal, or terminating decimals that don't go on and on forever. So those are two words we may have not heard. We have repeating, which is an easy one. You've heard things that repeat, they go on and on and on forever. And we have terminating decimals, meaning they stop. Like if you're terminated from a job, you don't go to that job anymore. You just stop going to work because you were fired. Hopefully that's not me or Mr. Campbell this year. So, anything you'd like to add to that, Mr. Campbell?
Yes. Thank you for asking. If I'm trying to figure out if a number can be written as a fraction, there are some ways that are easy to see. Like if it's written as a fraction, it can be written as a fraction. But there are also other things that we need to make sure we don't forget. Like if I put the number 4, can you write that as a fraction? Of course you can. You put it 4 over 1 and it becomes a fraction. You can also look at a decimal, like a 0.2, and you can ask yourself, can 0.2 be written as a fraction? And if you're not sure, you can use your calculator. Behold, you open your calculator, and you can type in 0.2. This is going to be practically magical for some of us. Like this could be a big moment in calculator life. Check this out. You can type in 0.2, and when you press enter, guess what happens? It says 0.2. That did not help us, but I knew that. I was joking. If you type in 0.2 and you want to see if it looks like a fraction, you have to tell your calculator to try to put it into a fraction. There's a little button over here off the side of the screen that says math. You can press math, and then you have to pick one of those random numbers that looks like it might turn it into a fraction. I'm going to pick number 1, turn it into a fraction, and it will tell me that it is 1/5. So that means that number, 0.2, can be written as a fraction, which is good news. Ms. Walton was talking about repeating numbers being rational. Here's what she meant. If I type in 4 divided by 3, can that be written as a fraction? Well, just did. But what if I press enter? Look at what it tells me. It tells me 1.33333333. And here's where the root word that she was talking about behind the word rational comes into play. I can look at this number and I can predict what's going to happen with it because it makes sense. I can say, hey, Miss Walton, this screen only shows like 10 decimals. What number do you think would be way out here at 20 decimals?
Probably a 3.
Probably a 3 because you can see some kind of pattern happening that tells you it's just going to be 3s and 3s forever. Now, the difference that would be different than that would be something like this. If I typed in square root of 8, and Ms. Walton's going to talk about this in a minute, 2.828427125. If I asked all you guys, what number do you think comes next? None of us have any logical reason to be able to figure out what the next decimal would be in that line because we don't see any pattern. So if you see a number that's already written as a fraction, or it's a whole number or an integer or anything like that, or you can see a pattern in it of any kind, that means it's rational. Even if it's a weird pattern like this. 2.125412541254. That's a weird pattern, but it is a pattern, and that means this could be written as a fraction, but we're going to check it just in case. Math, turn it into a fraction, enter. Now that's not a pretty fraction, but it is a fraction. That means it's rational. Back to Miss Walton.
All right, thanks, Mr. Campbell. So going with great definition. So moving to our next number, irrational. So this is what Mr. Campbell touched on, saying cannot be written as a fraction. These decimals go on and on forever and don't have a pattern. So I'm going to pull that calculator back up. I'm going to, again, so we did the square root of 8. And again, you wouldn't be able to know with any logical description what the next number after 5 would be. So another way you can check, just like Mr. Campbell did, so when he took this crazy long decimal here and pushed math 1 and then pushed enter, it gave us a fraction, right? So I could even take this decimal and do the same thing, math, and my decimal stayed a decimal. So that's just one more way to check. If I wasn't sure if there was a pattern, maybe I thought there might be, you can use your calculator to go ahead and check that for checking for if it's an irrational number. So this decimal is, if it turns into a decimal, it's going to stay a decimal forever and ever and ever. All right, our next definition is integer, and that is our positive and negative numbers, but no decimals. So this is where I want you to think number line. So on a number line, we have, not negative, 1, 2, 3. So we could go all the way positive, but we also have to include our negative numbers. So when you think integers, I want you to think positive and negative numbers, but no decimals, just those initial numbers that I've written here. And whole numbers. So this is where whole numbers, if you think of whole numbers, no negatives and no decimals. So if you think of a whole, so if I write whole like this, I was never in a spelling bee, so don't judge me. But we could spell whole like this, or we could spell whole like this. And a number that has a hole right in the middle of it is a 0. So I want you to think that whole numbers have a hole in them, like 0. Those are the numbers that are going to be included in our whole number category here. So we can't have any negative numbers and we can't have any decimals as well. And then our natural number is our last.
Miss Walton, I have a question.
Yes.
Are you saying that 0 is the only whole number, or are you just saying that 0 is the only number that we would ever, I don't understand. Okay.
So our whole number is going to be numbers that start with 0 and get larger, but no, you can't have any decimals with them. So meaning it would be 0, 1, 2, 3, on and on forever. So no decimals, no negatives. And since 0 is neither positive or negative, that is where we start with our whole numbers.
Okay, thank you so much.
And our last and final category is our natural, most inner set of numbers. Is it a category or is it a set? A set.
Categorical set.
A categorical set is our natural numbers, which tells us that positive whole numbers that do not include 0. So, Mr. Campbell, what is a positive whole number that doesn't include 0?
My age, 38.
38. So, if I were to put 38 here in the inside, we have a positive number that doesn't have any decimals. I guess that's not part of the definition. And Mr. Campbell, is your hand, can you put your hand in front of the, if I say to hold up one finger, you have 1, now 2, 3, 4, 5. Okay, and unless I chopped off Mr. Campbell's fingers, he can't hold up 0 fingers because he still has them on his hand. So your hand is a natural thing, and you start naturally counting with 1, 2, 3, 4, 5. And that is
And pass. Reset the page. And letter A on your note says write a number you think could fit into each category. So that's up to you to do. Meaning you've got that box on your page. So you look at this box and you write one number that you think would fit into each one of those categories. Then place these specific numbers right here where you think they should go. And whenever you do this, you want to put them as far into the chart as you can. Here's what I mean. Looking back here. If I use the number 8, well, 8 is a real number, so I could put it up here in rational numbers. But it's also an integer because it's a positive or negative number, so it could be right here. And it's also a whole number because it's not negative, it doesn't have any decimals. And it's also a natural number because it's a positive whole number. Now, instead of writing 8 4 times down the line, just put it in the most specific category you can get it to, which is the natural numbers category in there, right? And you just, for each number you choose, put it as far into the system as you can. If you ran into something a little bit different, like, I don't know, negative 4.2, it's not a natural number, it's not a whole number, and it's not an integer, so it would only fit out here into the rational category because it can be written as a fraction, and none of these other characteristics apply, so you're good sitting that in rational. But with a lot of numbers, you're going to have to move them further and further inside the chart. As you place these numbers, put them into the chart. Class conclusions, where does the negative 2 belong? I would put it, well, I'm not going to tell you where I'm going to put it yet, sorry. If you haven't put these into the chart on your own, pause point, pause it, work it, put them in the chart. Now, unpause, where does the negative 2 belong? It's going to belong as far into here as we can get it, which is going to be integers. It's not a whole number because it's not positive, but it is a rational number. So the next question says, how many categories could we place it in? I could place it in integer, rational, and real, because whatever is true in here is also true outside of it. On we go. Does the square root of 3 seem rational when you put it in your calculator? What about 1/3 or 7/2? What's the difference between them? And I'm not going to answer that for you. What I'm going to tell you is punch those into your calculator and look for patterns. If you see repeating decimal patterns, then it's rational. It makes sense. It is something you can predict what's going to happen later down the line. If you don't see any pattern, then it is irrational. Moving on. If a number is a natural number, how many other categories will it fit into? You look at the chart and you see how many categories surround a natural number. Name all the categories or classifications and give an example of a natural number. You can do that on the chart. Here's a good question to dive into. Can a number be rational and irrational at the same time? Think about that. I hope you noticed that on the chart itself, there is a line separating the irrationals from the rationals, and nothing can cross over that line. So the correct answer to that question is no, it cannot be rational and irrational. It either can be a fraction or it can't be a fraction. That's all there is. Letter C, as the categories get pickier, what do you notice happens to numbers in those categories? And I would say they just get a little bit more specific, and this is not mathematical, but I think it is kind of helpful to us. They get a little easier to deal with. Like the further you get inside the categories, all the way into whole and naturals, they become 1s and 2s and 4s and 5s, which we just tend to like better than negative 32/42, which would be a rational but non-integer number. What type of number fits into the most categories? Like the 1s and the 2s and the 3s, the counting numbers and stuff like that. What type fit into the least number of categories? Like the irrational numbers, the crazy ones that go off with all those decimals and stuff like that. And then right here, you've got a chart, another chart on your notes that we haven't used yet. And your job is to place these into that chart. I'm not going to write them up here in the right place on this screen, but you also have the answer key of the notes, and you can go back and check yourself, make sure you put them in the right place. Last thing is going to be this. This is what we're going to be doing in class, is picking these numbers one at a time and putting them on the hot seat and saying, okay, where does -4 belong? If I can put it as far into the system as possible, where would I put it? You know, and you can just start by thinking, gotta grab the 4. Is it a real number? Well, yeah, it's gotta be. Is it rational or irrational? Can it be written as a fraction? It can, so I'm gonna put it in rational. Is it also an integer? Is it a positive or negative number without decimals? Yeah, it is. Is it also a whole number where it's positive counting up from 1 or from 0? And the answer is no, it's not positive. So the deepest I can go into the system is right there, integers. That's -4. Now we look at this one. 2.36567, so on and so forth. There's no pattern I'm seeing so far, just a bunch of decimals moving through in different formats. So is it real? Well, yes, everything we're doing is real. Is it rational or irrational? And it is irrational, so that is all I have to do with it. There's no little categories below that to put it in. I do want to point out that we need to remember 0.7, well, I'll just put it right here because it's being covered up. 0.7 has that line over it. That means there's a pattern happening. The pattern is a 7 forever and ever and ever. Also like to point out that this number right here, 3.451, it ends. Like there's no numbers after that, which means it is no longer showing more decimals. What was our fancy word for that, Miss Walton?
Terminating?
The terminating, yes, like the Terminator, like things end. If you get terminated, it's over. So that decimal terminates, it's done for, so on and so forth.
So wait, if pi is 3.14, so all my teachers in the past have said pi is 3.14.
Yeah.
So if pi is 3.14, then if you just put 3.14, that would turn to, I could turn that to a...
I could turn that into a fraction. So that means pi must, oh, I didn't do that right, 3.14, math, fraction, boom. So that means pi must be rational.
Yeah.
Except it's not. Don't believe it. It's a lie. Because pi isn't really 3.14. That's like saying the Cowboys are winning. Sometimes it's true, sometimes it's not. Pi is really a whole bunch of things that just keep going forever. Look at that. 3.141592654, so on and so forth for millions and millions of decimals. But what some people do is they just abbreviate pi and say, well, really, pi is just 3.14 and they ignore the rest of this. But here's the deal. If this was my money, do you just want a little bit of your money or do you want all of your money? I want all of my money. So I'm going to take all those decimals and that's what I'm going to use for pi. And so when I look at a thing like this, I say, well, pi has decimals that go on forever. Is that rational or irrational? And that's your job to make sure you do right. That is the end. If you can soak this up and understand it, then you've got covered what we're doing Tuesday and Wednesday in class. Miss Walton, you got anything to add? Okay, so coming up, yeah, thumbs up for Miss Walton. Coming up, like on Thursday and Friday, there'll be some practice things that you have to do. And one of them is going to be on a Google form where you got to turn in, you got to put in your answers, and it's going to grade it for you and stuff like that in quiz format. So if you have any doubt on whether or not you comprehend all this, go back to the video again, watch it carefully, because again, I think what we can confidently tell you is if you understand everything we've just given you, you're going to be good for Thursday and anything that we have to move into after that regarding ordering numbers. That's it.